Good evening, everyone. Thank you for joining us today. My name is Fatma Al-Meheri, and I'm part of the ADIA Lab team. I'd like to welcome our speakers for today's session, Professor Thorsten Hoefler, Professor of Computer Science at ETH Zurich, and also our ADIA Lab Fellow. We have Khalid Al-Naimi. He's an ADIA employee, but also a KU PhD candidate. And we have Long Kang Lee from MBZUAI, a PhD candidate. Thank you.
Okay, thank you very much. So yes, I'm Thorsten from ETH Zurich. I'm very honored to be here. Thank you very much, ADIA Lab, for organizing this. This is a wonderful meeting. I've been here multiple times, and I'm always enjoying. I have spent a wonderful night in the plane, and it was too short to sleep. So keep that in mind when you listen. The other thing I keep in mind, I was promised a 60-minute time slot. So now we kind of lost 10 minutes, so I hope that I'll stick within. And the last introduction to this talk is going to be a journey. I'm going to tell you kind of my personal journey, but also the world's journey through LLMs and how it happened and where it goes to. So I'm trying to focus on this. And since I'm a professor, I usually start very early on, so the Stone Age. Right? So no, that's just a joke. So basically, as humans, we went through multiple developments, and you can see it's an interesting path that we went through with humanity. And there is one checkpoint that happened in the Industrial Revolution that I want us to think about. Because at that time, basically, human physical strength was superseded by machine strength. Basically, at the end of the Industrial Revolution, we were able to build machines that assist such that human domination, was not based on muscles anymore. We were not attacking each other. This is a bad example, I know, but that was kind of the thing with clubs. We were attacking each other with tanks. So that is something that I want you to keep in mind, because as we move forward in human development, we went into the technology age, the atomic age, the space age, the digital revolution, and here I come in, or many of you also come in, probably still remember what happened, right? We had a digital computer. We then started to connect all these computers, and this connection of all these computers enabled us to collect the vast amounts of data we have today. It's the internet. And basically, we use that internet in order to train very large language models. That is all the data that humans have generated through the connection of our worlds. I think this is a very foundational insight. And now the question is, when will human creativity and intelligence be superseded by machines? And this is the question I'm not going to answer in this talk, but I'm going to answer that it's a when and not an if. And I want to make the point, I want to make you all believe in how we get there and that we can get there. But first of all, I want to start, well, the talk was called the age of computation. Many people say we're in the data age, but actually I believe we are surpassing the data age. We already left it and we are entering the age of computation. We've already entered the age of computation. So what does that mean? Well, who knows that company? I'm not asking the question who owns any stock in that company ever. Most people know that company, and you look at the market capitalization until yesterday, it was a $3.5 trillion company, and it's actually still the second largest company, so it's not that bad. So it's had the fastest growth in human history of any measured company. Right? So it was not the fastest company ever. That was the East India organization, but that grew very slowly. This company grew literally within 10 years from $0 trillion to $3.5 trillion. And that's a zero down there. It's literally zero, like rounding error. Okay, and this company builds compute accelerators, explicitly not data storage. So that's an indication that we're actually in the age of computation, because this company purely deals with computation. There's more indication here. So Sam Altman last year already said that, well, AI models in February last year, 1 year ago, they're producing 100 billion words per day. All of humans only speak 1,000 times more. Now the adoption today is much, much, much larger. So probably AI models today already generate more spoken words or written words than all of humanity together. So think about this. This will actually lead to us running out of data. Like researchers have predicted, 26 will be running out of data because we basically have trained, we have consumed all the data on the internet. In fact, it already happened. So that's already in the past. So we moved much faster than people were thinking. And now it comes saying, we can actually generate synthetic data. Great, so let's go here. And actually synthetic data could be better than real data. So let's keep that in mind. Because what we want to do is we want to truly amend humans with creativity, with science. Because what is the definition of science? In German, science means Wissenschaft, which literally stands for create knowledge. Right? So if you're a German speaker, you'll relate. If you're an English speaker, just believe me. So now, what if we wanted to build an AI scientist? What if we wanted to build an AI system that helps people like me? I'm a scientist. My job is to create new knowledge. My job is not to repeat existing knowledge. It's creating new knowledge. So now we will see how to get there. One of our fundamental contributions in my group is this graph of thought, which is kind of a way to get there. Right? So now all of this is computation. And how could I give a talk in Abu Dhabi without saying something about oil? So computation is actually the new oil. But the nice thing is, I'm Swiss. We now have oil in Switzerland because we have the largest, most capable open science infrastructure for AI training in Switzerland. That's the Alps machine, 11,000 Hopper GPUs that is there for open science. Okay, cool. So let's move in this age of computation. But I couldn't give a talk on the 28th of January, 2025 without talking about the 27th of January, 2025. So biggest market loss in history. And I also couldn't talk to ADIA, partially ADIA representatives, who are probably a bunch of quants in here in that room. Biggest market loss in history, like nearly $600 million lost in a single day. How did that happen? Well, yeah, 586, so something DeepSeek. Okay, what is this? Well, actually, DeepSeek, again, it's more than $1 trillion loss. People are speculating nearly $2 trillion total loss to tech companies in the United States. What is happening? Well, what really happened is they released this report. The funny thing is, they released this report a month ago. It took a month for the market to react. And then the market reacted over a weekend. Well, that's the power of Twitter or the power of social media. It just started trending, but this is actually quite old. What did they do in this model? Well, they actually released a model, an open source model, where they said, well, this is now an open source AI model. You can download it, you can test it. People tested it. This is why it took a month. People convinced themselves, people like me. I have a live demo. Damn it, I don't have a live demo because they don't let me use my own laptop. I would have a live demo if I would be able to use my own laptop. But you can download this model, you can use it on your laptop, and you can run it. And the interesting thing is this model performs about as good as GPT-4o, which is driving ChatGPT in the background. So you can see it here in the statistics, probably a little bit small, but just believe me. But that's not the thing that crashed the market. The thing that crashed the market was they claim that they spent about $5.6 million to train that model. And now everybody is like, well, if this Chinese skunkworks thing can train the model as capable as the largest, greatest model for $5.6 million, why is everybody buying that stock of that big company that provides compute? Actually, I believe that the market is overreacting here because I'm going to convince you in the remainder of the talk that we have a very interesting case of Jevons paradox going on. Because the moment this price will drop, there will be more demand. And this is what the remainder of the talk is about. So it actually, the recent happenings fit perfectly. But now, still interesting. So there's this doubt on billion-dollar spending and blah, blah, blah. And at the end, you can reason about this yourself. The owner of the company, DeepSeek, is a hedge fund manager. Now, if you're a quant, you would know how to react to that press release here. Okay, no further comment. So yeah, some of you got it, right? It's called short. Okay, so now I want to give you this, as I mentioned, the personal journey that I went through helping big companies to succeed in that world. So really from LLMs to AGI, and it started all 2017, so not in the Stone Age. It's actually all extremely young. And what started in 2017, there was a paper release that's called Attention is All You Need, which is it's actually an effort by Google at the time to parallelize RNNs or LSTMs, recurrent neural network, long short-term memory networks. They were hard to parallelize because of the recurrence. What they did is they just said, oh, let's throw the recurrence out and just use attention. There was an experiment to parallelize stuff. So parallel computing is cool again. But it led to something that's much more powerful than they initially thought. So this is the computational structure. What did it do? Well, actually, I mean, it has a bunch of components, but these components are close to trivial. Like I can explain this to your grandmother in about 2 hours what this thing does, and you will be able to reproduce it by coding it in Python probably in 3 days. Right? So this is a very, very simple thing. What it allows to do, it allows to feed the original version, we're feeding in text, and it was translating text to another language, for example, here from English to German, and then it gave you the most likely next word. And again, if you're a German speaker, you will appreciate this. If not, just believe me that the percentage is right. Okay, so now, again, you can explain this to your grandmother. It's literally 3 simple kernels that this consists of: matrix multiplication, layer norm, and softmax. That's it. Don't need to do much more. 95% of the flops is matrix multiplication. It's a great fit for HPC GPUs. I would actually credit HPC here, that HPC led to the creation of devices that were extremely capable for these floating point computations that later turned out to be a good vehicle for AI. So I would really credit people like Horst and also Jack Dongara, who contributed to launching that effort. So easy to parallelize. At the end, it's a little bit more complicated. I don't have enough time to go into details. It's all about tokenization. Like, you need to find the right representation of the language in the right vector space. But it's vector space. It's matrix multiplication at the end. So, I mean, computationally, it's very, very simple. But there's a lot of things to be said in addition to this. I'm a big fan of tokenization, so we can take this offline in case you want to talk about it. That happened 2017. 146,000 citations on that paper. Crazy. So then 2018, BERT came. Bidirectional encoder representation of transformers. It's basically taking this idea, these transformers that are translation devices, and don't train them on a translation task. You train them on a task where you were omitting a word and had the model reconstruct that word, bidirectional from both directions. So that was the first shining light where people were looking at and saying, oh, this is not just a translator. This can actually develop an understanding of grammar, an understanding of not just syntax, but also semantics of languages. And by understanding, I mean, it could replace the right missing word. That's what understanding for computers means, like a programmatic way of dealing with it. People at Google were shelving that thing. We're basically saying, oh, that's nice. Okay, yeah, let's do something else. Then another little company came, OpenAI. They said, huh, you know, if we put this to work in a generative manner and not have holes in the middle, but actually holes at the end, and it auto-completes. We do an auto-completion network that is a semantic autocomplete. With that semantic autocomplete, we will actually be able, that was the vision at the time, we will actually be able to really lead to something bigger. That was a big bet. It was extremely expensive. They trained GPT-2, and they found these things are unsupervised multitask learners. What does that mean? That's a little bit gibberish. We'll get to this, but it basically means that they could complete arbitrary sentences. For example, the capital of the UAE is, and then it would fill in the most likely word, which is, of course, we know, right? So, and this is now a multitask learner, right? So you would have to phrase everything as a completion task, basically. So then GPT-3 came, same thing. And they basically said, this kind of the same thing, language models are few-shot learners. What's a few-shot learner? It's similar to a multitask learner, but the way this works now is you give multiple examples to the model, like poor English, good English, poor English, good English, poor English, and then you ask it to complete the good English sentence. So now, in addition to just the autocomplete, you give it more examples. This is going to be very important later. So what happened then is that they realized if we increase the size of these models, this is now the proxy for the size, the validation loss, which is a measure of quality, goes down. So the lower, the better, right? So this was the beginning of the scaling of compute. This was the beginning of that uprise in the NVIDIA stock price, okay? Because they are the compute company. It's a good proxy to measure, but the whole market was pulled along. So this is the number of petaflops per second days that is needed to train a model here. So that basically means one of the largest supercomputers on the planet that I was involved in, the Blue Waters machine, was a sustained petaflop machine. So there was a $500 million project, US dollars, where we fielded the machine, and that was doing about 1 petaflop per second 1 petaflop per second, right? $500 million. Total cost of ownership, lifetime was about 5 years. So $100 million per year. So now this is petaflops per second per day, days, right? So you would basically need that machine for 10 to the 0 for 1 full day exclusively to train your model. That's 100 days, that's 10,000 days. Okay? Of course, Moore's law went further, so computers got faster, but that's an extremely expensive endeavor. This is why all these curves stop here. Okay? What they also found is basically more money. You throw more compute money at it, your model gets better. Also, more data. It's the same thing. Tokens is just the amount of data. More data at it, great. What people then found is that they found scaling laws. They basically found that, hey, the optimal model size grows smoothly with the loss target and the compute budget. So in other words, the more compute budget I put at it, the better the model gets. Right? So that's a nice insight. And then suddenly, that was the beginning of the supercomputer era in AI. So suddenly Microsoft says, okay, we're putting in $1 billion because we can into this endeavor, throwing lots of money at it. There's even a comic about the CTO in front of a supercomputer. This is the first time in history that large companies, large private companies, large private corporations that are made for profit embrace supercomputers at a big scale. Because before it was a government effort. You wanted to simulate scientific computing and things like this. But now it's an industry thing, big investments. Google built a supercomputer. Google, a search company, built a supercomputer. Facebook, like a media company, essentially, social media company, builds supercomputers. Tesla, a car company, builds supercomputers now. Everybody builds supercomputers. They invest millions of dollars. Actually, if you just look at the 2023 orders of NVIDIA devices, Microsoft and Meta, they ordered 150,000 each. Each of these devices is about $10,000. You can do the math, what that alone in device cost is, and they haven't connected them yet, right? 2024, because now it's 2025, 2024, Microsoft nearly bought 500,000 of those. And now, interestingly, number 2 is ByteDance, and Tencent is number 3, Chinese companies, right? So not the case anymore in 2025, unfortunately, but well, Meta and then Tesla and then all of these companies I mentioned before. Microsoft just announced a couple of weeks ago, January 3, that they invest $80 billion into infrastructure. $80 billion, that's crazy. And actually just last week, of course, $500 billion on the table on a project called Stargate. I'm not sure if that money really exists, but so that is the ambition that people have. So now we take all of this. What are we doing here? Like, what is this doing? Well, at the end, it's really what I mentioned before. We take text off the internet, right? We remove a word, we run it through a computational structure, we get some probability distribution of possible outputs, right? This is what the computational structure outputs. It would actually output a table of 128,000 different possible words here, or word pieces, but I only have space for 7. And then, of course, you know what the right one is that you removed, because you removed it in the first place, you can just remember it. And then you update this computational structure to next time you run it, you will have a closer output to push the real word you removed closer to 1. Like, that's the algorithm. It's a 40-year-old method, and you just do this a lot. Like, nothing really fundamental changed here. The computational structure is this transformer thing. So this has been trained on the whole internet. We are talking about extremely large models. These are 1 terabyte just to download these models, so extremely large models. And they take weeks to train on very large computers. But this is really what these supercomputers do all day long. They crunch these numbers to learn statistical distribution of language. So now the nice thing is this, it turns out that this is quite expensive, because if you look back at 2019, you look back at the cost that was projected that OpenAI took to train GPT-3, it was about $13 million or $12 million to train that model, like a single run. So that's now obviously down to 5.5, but yeah, sure. So that's interesting. And now if you look at the computational structure, and by the way, there's a funny thing to be said about this. There's a bug in the training. If you read the GPT-3 paper, they kind of admit at the end, oh, we have a bug. Oh, man, it's not so great. They couldn't fix it because it's in there. You have to work around the bug. It's not too bad. But now if you look at the actual computation that happens in this model, it's 99.8% matrix multiplication. That's it. Like, Hale, Jack Dongarra, top 500, great. That's what these GPUs are really good at. That's what they're built for. Highly optimized. What now turns out, unfortunately, is that the 0.2% of the operations, they take about 40% of your runtime. So there's a disparity here because they're not highly optimized, right? And so we exploited that in one of our works where we basically looked at the data flow, because those are not operations. Those are just data movement. They move data. They copy data from across the chip and things like this. So we improved that part in my research group, and we found that you can actually reduce that by 75%. And this gets you about a savings of $3.6 million just alone for the GPT-3 training. So that's a huge impact. So I can now explain how this works, but it's relatively simple. So we phrase the whole thing as a data flow graph. This is a transformer in a different view. We run different permutations of the data layout. So the way you serialize these matrices into main memory, you can of course permute them. They're all 4-dimensional, so you have all the different options. And we do different loop fusion strategies. That's also a technical detail, very, very simple. Then we build a large graph to understand what is the best configuration of the code configuration of the layout in memory and the fusion of the loops together. And then we get the overall best result out of that configuration graph, and then we get the speed up. Right? It's a relatively simple approach. This is all in production today. So every single GPT model follows kind of these principles today. Of course, if you can get this like 30% cheaper, you would totally do it. But now, turns out that reducing cost is extremely important. Right? So now we're going back to this, because what's happening now? Well, first of all, 2022, just 3 years ago, ChatGPT entered the game. Like in this time, it feels like this thing has been around for ages, isn't it? I mean, many people cannot imagine a world without ChatGPT, and so it was only 2022. It was trained based on RLHF because this model here that it was based on was just to complete the next most likely token model, like I mentioned. This is not a good conversational partner. This is a really annoying conversational partner. This is like people you don't want to talk to. But now with RLHF, reinforcement learning based on human feedback, we specialize that model to become a nice, pleasant chat agent, also not to threaten to kill us. So that is a nice way. It's actually exactly like you would train your child. You would have your child say something, and if it's wrong, you slap it, and if it's nice, you give some reward. And this is exactly how RLHF works, right? So there are humans judging the output of these models. If they don't like it, down. If they like it, up. Today, that's, by the way, direct preference optimization. So that's an optimization to RLHF, but that's a detail. But this is how we got to a chat agent. So lots of human supervision, making this nice. And now that got interesting because ChatGPT was also one of the fastest growing services ever deployed by humanity. Well, of course, if you give something useful away for free, then it grows very fast. But now, suddenly you needed to make these models that are extremely big. You needed to serve them to millions of people at basically overnight in 1 month. So how do we do this? How do we turn this thing into a business now? That's different. That's not research anymore. That's a business. And by the way, at this point, Google realized they shouldn't have shelved BERT. They were like, oh, that was maybe not a good idea. So, well, you know what came next. But now there comes another company in the game in this timeline. Because at this point, ChatGPT was established as the brand. So you couldn't fight the brand. It was close to impossible to fight the brand. How do you fight a dominant brand in 2022? Well, what you do is you have everybody on the planet fight that brand. You open your model as open source. You distribute it to everybody, and now everybody's going to compete with a model, right? So that was a strategy that was also very clever. That really tightened the market. With the advent of these Llama models and later Quen and then DeepSeek, which is another model in this category, they put a lot of pressure on the providers, on the commercial providers. They need to reduce cost. How do we reduce cost? Because suddenly you had an alternative. Reduce cost, you made smaller models, you optimize the models computationally, or you reduce the hardware cost. Right? These are the avenues to go here. And what we actually mentioned here, in this part, the talk is called 3 eras. At the beginning, we had the era of model size scaling. Right? We made models larger and larger and larger. But if I'm now serving models to millions of customers, I don't want this. I need small models because large models are computationally expensive. They do large matrix multiplications. Very bad idea to serve this. So what suddenly happened is we now want to make the models smaller. How did we get them smaller? We fed them more data in the supervised training approach that is called distillation and sparsification and quantization and many of these things to perform better at less computational complexity. Right? So this is the second era in our long overview. It's the era of data scaling, and it's even more training compute because now you train a very large model and then you spend a whole lot of compute to make it smaller. Right? And it costs a lot of compute to make the model smaller. It's not trivial. Now, optimization of these systems really became the driver for the future. At this point, it was clear. Like this was when NVIDIA crossed the 2 to 3 trillion mark. It was absolutely clear. So that was about 2023-ish, right? So if you look at it's very much tracked by the stock price. So now we need a scientific approach to it, right? So this is where I come in. I'm a scientist who looks into these things, and so I will give you a little bit of an overview of how you make these computations 1,000 times faster. I told you at the very beginning, we did something like 40%. That's great. But here you need heavy artillery at this point, because if you want to serve it to millions of customers, there's a much larger pressure. So I'll give you actually not 1,000 times faster, 1,000 times cheaper, like 100 times faster and 10 times cheaper. So now we already realized that moving data is the most expensive thing in this, right? So, well, couldn't we shrink the data? Right? This is question number one. And the answer is yes, because somehow all these models are trained with a data type, with a number representation that's called floating point 32. So that means a floating point representation with 32 bits. So now, why is it floating point 32? Well, it's mostly technical reasons. I can explain this in great detail if you want, but it's going to be a 2-hour talk itself. So I don't have that much time. We can talk about this offline. The interesting observation is, not saying it has anything to do with this, is that my brain can differentiate 24 voltage levels, which is 4.6 bits, right? Cool. Now we have 540 billion parameters. We can actually get this down, and we can round this to smaller number of bits. And this is how, if you download a model today through Ollama, if you download Qwen, for example, it most likely uses the method that we contributed at GPTQ to quantize this model to about 4 bits or 6 bits. It really depends which version you download. But I could explain this now, but since we are running a little bit short on time, I will just skip this. So you really look at the expansion of the loss function. You do some mathematical tricks. You look at which parameter to round. You round them in a specific order to minimize the overall error of the rounding. But at the end, it's a rounding business. So you're rounding in a 540 billion dimensional space, which is a lot, but it works really well, especially if you phrase it as a nice mathematical problem. So you can actually phrase this as this optimization problem here. So you want to minimize it's very simple. You want to minimize the error that you make when you take the original version minus the rounded version squared. Right? So if you minimize this, great. To solve this, you need the inverse Hessian, which is a matrix of size 540 billion times 540 billion. There's no computer on this planet who could even store it. Even all computers together could not store it. So you have to approximate this thing quite massively. And if you care about this, you can read the paper in great detail. So I don't have enough time here. That gets us 10x. Because we went from 32 bits to something like 3 bits. Great, 10x are here. How do we go further? Well, with sparsification. So these brains are not densely connected. So now not all features are always relevant, like the future will be sparse. You can totally read this here, no problem. So now, this is more complicated to explain, but at the end, I can tell you that many of today's models can be heavily sparsified, so to 95% sparsity, which means we can remove 95% of the values and they still kind of work. Large language models, we can get to 70% today without loss. So we are still fighting this. This is still an active research topic. You can read the paper we wrote on this, very, very long. There's a YouTube talk, actually. That talk itself is 2 hours explaining how sparsity works. I don't have enough time to summarize this. By the way, these two things combine. Sparsity and quantization go together, and then you get a joint benefit of 100x. Sparsity, if you discard 90% of your values, then you have another 10x benefit, right? Because every 10th value is only active. So now you get 100x. Cool. But now there is another 10x we are getting out of a principle where we develop a new compute system to do so. Standard data centers use topology in the computer, the way they connect computers, that's called fat tree. That's a very wasteful topology. It is extremely expensive to build. Google introduced a 2D torus at some point. That is too underpowered. That's extremely cheap, but too underpowered. At the high level, what we did is we combined the two into a flexible, scalable topology where you could scale like 2D torus components, but still connected by switches. Like that's the high level view. That saves another 10x. So that is great, and that's also production. So now we had the 1000x gain. So great. I'm aware that I did this very, very fast. I covered parts of that last year in my talk, but there's a full talk here that you could watch. I just wanted to summarize this again in like 5 minutes. But now back to now we have the 1000x, but now back to the timeline. So we are now here, 2023. A lot happened since 2023. It seems to be exponentially increasing. So What happened then? Actually, just last year, Ilya Sutskever was saying, well, we are at the end of data. We have no data left in the internet that these models haven't seen. It's very true, actually. There is no data. Like you just have put everything in. And you can see this by the performance of these models partially. So who has seen this plot before? Some people are not too many, but this plot is quite amazing. I mean, when I saw it first, I was scared for a minute, and then I was like, yeah, it's going to be fine. So this is a human exam test. So you take double-blind you have a double-blind experiment. So you have these exams here, and you can see this like world history, verbal, biology, microeconomics, writing, I don't know, blah blah blah, exams, human exams. And then you put these models at a test, and this is let's ignore the green and the blue. Just let's look at the uppermost thing, which is the best performance, and you compare those with humans. This line, black line, is the average human. It's the 50th percentile of human test takers, like how they score, and they were graded by professionals, like you grade your exam, right? So you can see that for most of the tasks, these AI models are better than the average human performing those. Not better than the expert human, but better than the average human. Okay, that's interesting. So now, what unifies these tasks is that they're actually quite simple. There are very often, like many tests, they retrieve knowledge. You have to know a certain thing. So what we can record now that in about 2023, these language models were generally extremely good as a general knowledge operator. Like you could retrieve facts from them. And this is nice because they trained the whole internet. I mean, what would you expect, right? If you would have time to read the whole internet, you may be able to compete with the network, but you don't have time to read the whole internet. Like that exceeds your lifetime or our cumulative lifetime. So now the only thing they couldn't do was reason, because remember how they're trained. They are trained to complete the next word with the most likely occurrence in the internet. Right? So if I tell these models, please sort the following 5 numbers, it would fail because it wouldn't have seen those specific numbers on the internet. Like it wouldn't know how to do this. How do we get to these models today that seem to be relatively smart? Well, that's a new category of working with these models. So what I described so far was basic input-output. This is how most people work when they use language models. Like you chat with the thing. Like you put something in and you get something out. Okay, cool. Like sort the numbers here. And then we had a very interesting discovery, 2022. It's called chain of thought, which they really just discovered. Well, if I actually tell the model, to sort some other numbers, you do it like this. Like you basically give a recipe, and then you tell the model, hey, sort the numbers. Then they perform significantly better than before. So you give the model a chain of thought, like you would explain to your child. If you tell your child, sort the numbers, and it's a young child, it doesn't know how to sort numbers, then it wouldn't do it right. Right? But if you tell your child, well, to sort this set of numbers, you do it like this, then the child can template, match it, and do it again. That was a huge breakthrough that AI models, like nobody understands why, by the way, can do this. And it was even funnier when there was a paper coming out by a Japanese colleague where you simply tell the model, let's proceed step by step. There's a lot of memes about this. So you don't tell the model how to do it, but you basically tell the model, well, think a little bit before you reply. Okay? Because the model itself can look up this stuff in its database. Right? It can. You just need to give it a hint. Think about it. That is crazy. That's completely crazy. So what happened then is that people basically said, oh, okay, so we can run these models for cheap. We will actually have multiple chain of thoughts. We will just evaluate a whole lot of these thought trains, and we'll see which one is best. Then came, of course, the tree of thoughts, where you would basically have a thought, and you could split it into multiple sub-thoughts, and you could prune paths and stuff like this. And here comes our contribution, which is a graph of thoughts, which is like humans actually think I could have different thought chains, and then combine thought 1 and thought 2 into a new thought. Right? So that's graph of thoughts. This is how I think. If I solve a very hard problem, I'm actually coming up with sub-solutions, and then I combine these sub-solutions into a final solution. Like I need the combiner. In a tree, I can't do it. Okay, cool. So this is what happened 2023-ish, chain of thought. So now we're getting towards the end. But now the question is, I mentioned that you needed to input these thoughts somehow. how do we get to these thoughts? Especially, how do we get to these thoughts for problems that no human has ever solved, like healing cancer, something like this? How do we get to this? There is no step-by-step like rule on the internet how to do this. So how do we get to new creative thoughts in the models? And here I want to make a detour. First, I want to tell you that while you watch me speaking for the next couple of minutes, hallucination can be productive. Usually when you say language models hallucinate something is when they make something up that's not in their data set. Like they create some random thing. Usually people believe it's bad, but actually the
The room is mute.
No voice. Please switch on the sound.
Guys, whoever is in the room, please enable the mic again.
test. Are we back?
Yeah, works.
Okay, wonderful. Apologies, I don't know, I didn't do anything. I'm not feeling guilty here. Not yet. Okay, so we had this detour to 2016 where we basically said the game of Go, you can explain it to a 3-year-old. The rules are very, very simple, but the strategy you have to employ to win against a skilled player is extremely complex, right? So what happened is that actually Google was training a network to compete with the best human player, Lee Sedol at the time, 18 times world champion in Go. It's a serious business, this world championship. It beat Lee Sedol such that he quit playing Go. That was his profession. He stopped it right after. There's a wonderful documentary on YouTube, and I recommend you watching it. You will say, I mean, this is interesting. So how did they beat the best human player? Very simple. You take the state of the network, the state of the board, right? And then you define a function that's called a policy function that defines a good move, that guesses a good move. It really guesses it. It hallucinates a good move. It says, oh, let's do this. And then, of course, the first move may not be good, so you do this m times. So you kind of guess m good moves, right? Then for each of those moves, you apply another function, which is called a value function. You assess how high the chance of winning is if I perform this move, right? So what you do then, of course, you look at the state where the chance of winning for me is highest, right? Because otherwise it would be silly. Oh, genuine service alert. How do I get rid of this? Let me see. It's probably oh no, that's dangerous. I shouldn't have done this. Oh, you have the mouse. Okay. Learn more in English. That's a nope. It's disabled. I should have really used my own laptop. It's also okay. Yeah, let's. Yes, exactly. Okay. So now we play this game. Policy function hallucinates new moves. Then we go to the state that is the most likely for us to win. Then we hallucinate again m next moves. Then we assess all the states again, and then we realize in this particular example, hey, this was a dead end. We actually want to go here because 6% winning chance is higher. Then we expand this. Then we go like this, blah blah blah, and then we continue this for many levels. So what was the new idea in AlphaGo? This is an old strategy. It's kind of a trivial strategy. This policy function is a deep neural network. The value function is another deep neural network of the same structure with different weights. And then they just ran it forever and forever using MCTS. Right? So they just trained these two neural networks on rollouts of this game. So this was 2016. And now you can see where this goes. This strategy here is beating the best human reasoner. Right? It's the best strategist has been beaten by this machine. So now what we do, how do we get to a human thinker that solves generic problems? Well, like the problem sorting these numbers. I said the model didn't perform well at the time. Now they do. Well, you ask your policy function for your next step. Right? The policy function kind of outputs the next thought, the next step. For example, numbers are blue. Okay, that's not a great next step, but look up quicksort. Hey, that sounds reasonable if you talk about sorting. And then you see, if I play this example, oh, cool. So that's good. So then after looking at quicksort, what does quicksort do or how does it work? Now you can play this example as well, but maybe the model realizes, hey, applying quicksort is too heavy for just these 7 numbers. So maybe we just want to split them into 2 sets. Right? Maybe we just want to do simple divide and conquer like we learned in school. So let's do this and let's continue. The value function goes like this and so on. So basically now we play the same game just with real language. And as we know, our human language can encode arbitrary concepts, at least arbitrary concepts we can comprehend as humans. I'm not claiming that human language is universal, it's probably not, but whatever we can comprehend, I can express as language, right? So cool. Now, our policy function is a deep neural network, is a transformer network. Our value function is another transformer network. Did I mention that these are really expensive? Because now you have a problem. Like this is super mega expensive if you run this. Before I said we had 1,600 expansions in the alpha model. You cannot afford 1,600 expansions. There's no way, right? But this works. This is how O1 most likely was trained. This is how DeepSeek was trained, R1. This is how all these models were trained. So wonderful. Now we are at those 2024 reinforcement learning models talking to themselves, hallucinating solutions, rationalizing solutions. And again, unfortunately, I can't give you the demo because I would have shown you now the DeepSeek R1 model running on my laptop and showing you all the reasoning steps of the model, how it works. Right? So now I can show you, I have a backup, which is the Google version, which is a little bit older. So now if you look at the Google version, sort the numbers, exactly what I just told you. And now the model will it thinks. And it gives you a whole lot of steps. Like, oh, I do this, and I do this, and then it gives you a sorted number. First of all, we realized that was 6 seconds long. So to sort these numbers, it gave you 6 seconds, and it gave you all these, choose a sorting algorithm, merge sort, apply sorting, blah, 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 step-by-step mental sort, blah, blah, blah. So now the model itself reflects on what it's doing. Right? So there's a very, very powerful concept to this, and I can talk about this more offline. So this is quite nice. So now we have these reasoning models. And now it comes, what can these things do? This literally, they were trained with this MCTS mechanism, blah, 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 reinforcement learning, just more compute, essentially. Because, by the way, these MCTS trees that I showed you here, oh, okay, that's too much. These trees I can run forever. If I have infinite compute, I can just run this forever. It'll do something useful at the end of time. Okay, cool. So now we had this benchmark that just came out. Actually, an interesting development is that a couple of months ago, a set of researchers realized, oh, we do not, many of the math tasks have been solved. There's a data set, GSM 8K, grade school math 8K, 8,000 questions. And then some newspaper article said, oh, math is solved. These language models like mathematicians are a thing of the past. So mathematicians got upset. And they said, okay, we define now a benchmark that you cannot solve. That's called frontier math. That is like a benchmark I cannot, I looked at those and I'm not capable to solve those. So the average human is hard. And indeed, if you look at what these models solved, is basically 2% of these. They got 2% score, so nothing, I mean, close to nothing. Well, and even Terence Tao, like Fields medalists, said just like 2 months ago, 2 months ago, oh, these are extremely challenging. They will, for years, the AIs will have trouble. Oh. Yeah, like less than a month later, when 03 preview came out, 25% just at the first try. These reasoning models, they can suddenly solve extremely hard math problems. And now you may argue, oh, I'm not a mathematician. I don't care about mathematicians. It's fine. My job is safe. I rely on all kinds of interesting intelligence. There is another benchmark that's called the ARC AGI challenge. Who knows about that benchmark? So there are some people here. This is a very nice benchmark. I sometimes play it at night when I can't sleep because it's interesting. So here there's a score. So there is the score is here from 0 to 100%. So the average mechanical Turker, so underpaid workers that don't really pay attention, they do 75% there. The average STEM grad student does 98%. So smart humans can totally do this, right? These models are really bad, like less than 25%. So actually, if you look at the development of these models, until 2024, they were basically lower than 5%. Like GPT-4, GPT-4o was super bad. Here is when this MCTS RL mechanism came, the thinking mechanism, and it was boom going up to nearly 100%. Right? So this was a benchmark that was supposed to be only solvable by humans without any cultural background. We will do an example of that. So that's pretty interesting. So now you say, oh, I don't care about humanity. I'm a programmer. Programming is going to be safe. Well, let's look at the Codeforce ELO rating of this benchmark. So this is kind of like chess for coders. Like ELO rating is a game ranking. And so it goes from legendary grandmaster to newbie. Right? So you can play this game. I played it. I'm not going to give you my score. But you will be getting a score here. So 99.99% of the people are versed in the legendary grandmaster. You know, O3 is at the 99.95th percentile of all programmers who took that test. Okay, so there's a very low chance that we are better than this. So then you may argue, well, I'm a scientist in my field. There's a benchmark GPQA, graduate level Google proof Q&A benchmark. So basically, Google wouldn't be able to answer these questions. Yeah, human PhDs are 34% outside their field, 81% inside their field. O3 is 87% in all fields. Okay. That's interesting. So how did we get here? And it's clear that we got here, actually, if you paid attention. We took the superhuman strategy player, the best strategy play we know, and it beats all humans, essentially, in whatever game they play. We put it together with a superhuman knowledge database that knows more than every single human. So we combined them into one model, and that is the reasoning model. And these are reasoning language models. They're very different from large language models. This is the next generation. And we are now in the era of reasoning scaling, right? So, but there's one thing. Actually, we can play this. So this is the ARC challenge. This is how you play it. So you look at this, and then you look at this. So you have to see the difference, and you have to understand the algorithm that's used to compute this difference. So example 1, input, output. Example 3, input, output. Example 2, input, output. And now I give you an input, and I ask you the question, how many of these blocks are going to be colored blue? It's 1 here. It's 3 here. It's 2 here. How many is it here? Can anybody help me? Just shout a number. 6. Perfect. Chat, O3 fails with this thing. So congratulations, you're better than the reasoning language model. 6 is the answer. And if you care about how this works in detail, we just recently published a paper on 23rd of January, how this all works. There's an overview, blah, blah. If you care about the scientific details, it's just an overview talk about reasoning language models. So this is kind of a comprehensive way also for you to reproduce these things if you wanted to implement it yourself. Like you can just follow that and you would go pretty nicely forward. So now we're at the very end of this. So now we have these reasoning models. Okay, crazy. Now it gets interesting, right? More and more compute. So now, since we are here in a financial setting, I want to present some data as well to support my claim of these 3 different eras. So now let's look at the cost per 1 million tokens of the OpenAI API. Right? That's public information. We can just look at what they costed. Back in December 21, GPT 3.5 was $60 for 1 million tokens. Cool. GPT-4, as I mentioned, is a much bigger model than 3.5, so it's twice as expensive, right? Because they need more compute to run it for you. And then that was basically the era of model size scaling. So we went up. Then they quickly realized, okay, there's no market for that, so we need to make it cheaper. So they made these smaller models that are called Turbo or Mini. And then you could see basically here, lots of data, the data scaling pushing them down. More training, smaller models. This is the second era. And now the reasoning language models come back, and you're back at the $60 because now you need to run these reasoning chains, right? And I would have given you the example which blabbers on forever to just sort numbers. That would have been entertaining. There's actually a single task in O3 that costs $5,000. It's going to write books, like literally tens of thousands of tokens in order to solve that task. Like the model will write a book. An average book is about 5,000 tokens. right? And so it's going to write multiple books to solve this one task. It's crazy. So now what does this mean? We need more compute, we need cheaper compute. Here, this is where I come in. So I'm a scientist working on these optimizations, mentioned that earlier. The principles are data type sparsity and spatial. We need cheaper systems. What most people overlook is that this is actually a highly contended market. So this is very hard to get into this market. However, the networking market is wide open. So I want to talk a little bit about our efforts to build a networking structure, which is kind of converging data centers into supercomputers. Like if you build a data center today, you better build a supercomputer, because if your data center is not a supercomputer, you can't run AI workloads. So, and then you may have a problem. So we've written a paper about this a long time ago to foresee this. Let me skip this and just give you the high-level picture. So we formed a consortium that's called the Ultra Ethernet Consortium, where we define an interconnect and a network connection for AI systems. Like Ethernet, most of you know Ethernet, that's like the cable you plug into your computer. It's like wireless, runs over the Ethernet protocol, but we define a variant of this for AI workloads. So many companies involved, lots of white papers. So actually it's a very large thing. It's more than 1,500 members at this point. This is the view of the room where we meet and discuss this. I'm not on that picture because I'm the chair taking the picture. So I'm standing there, this is my laptop. This is my co-chair, Karen. So it's wonderful. We meet. We will have the spec out at the end of this quarter. So I could go more into detail, but I want to skip this because I want to leave more time for questions. But the idea is to define a hardware specification that vendors can have a differentiating factor to flatten the market. Because right now there's only one provider for these networks, and most of you know who that provider is. May have lost a bunch of billions last night. So there are lots of features I could be talking about, but let me just skip this. So there's lots of really cool system stuff, and if you care, we can talk about this offline. So just to summarize, I've told you quickly how to get 1,000x cost savings. I've shown you the whole history from transformers, the prehistoric era, to the reasoning models that we have today, and the reasoning models are carrying us into the future right now. This is what's happening. This is the hot iron. This is what dropped DeepSeek, because I was telling you the model actually dropped in December 27. However, 1 week ago, they dropped the R1 model, the DeepSeek R1, which is their reasoning model. And that convinced all of the experts that they know what they're doing, because that model is pretty darn strong. And again, I would have shown it to you live, because it's actually so strong that it runs on my laptop that doesn't even have, so strong in the sense of cheap and capable that it runs on my laptop without an accelerator. And really, that's the combination of these two superhuman strategies, superhuman knowledge, and now you need systems to run these models effectively, cheaply. Like, this is all a price question at this point, because we know that we will get to creativity. We just don't know how to pay for it. So now we need to optimize the systems. If you like these kinds of talks, we have a YouTube channel where you find all of this stuff. I've covered about 25 research papers here in this talk. So each of those has a 30-minute talk by one of my students on our YouTube channel, in case you want to dive deeper into anything. Thank you very much, and I'm open for questions. So we should have about 10 minutes. We started like 13 after.
Hello. Thank you for the talk. 2 quick questions. When you mentioned sparsification in the beginning, is that basically grokking?
Grokking is one mechanism for sparsification, but there is a whole lot of mechanisms. So I would not want to fix myself. Actually, simple magnitude pruning is the most effective one. Simple magnitude pruning is the most effective. You just cut the small weights. And fine tuning again. Yeah.
Thank you. The second question is, and correct me if I'm wrong, but if ultimately these language models are just compressions of a language, if it's just a very convoluted and complex statistical distribution of language, no matter how good it is at reasoning, it's still just next word prediction. So what's your view on neurosymbolic models?
Oh, that's an interesting question. So, yeah, that's hard, because I would have to tell a long story to answer that question. That would exhaust the 10 minutes. And I've already exhausted 30 seconds now by explaining it. So the short answer is, I believe neurosymbolic models have to form internally in the weights, in the activation progression through these layers, in order to do what they can do right now. The demo I would have shown is ask the thing to sort the numbers, And it actually shows very, very strong forms of reasoning to solve that task. And it outputs you the reasoning steps. And I would even call that neurosymbolic reasoning. You can now formalize this more. Like you can now really make it symbolic. Like there's no symbolic in that reasoning. But that's just an explanation. So in my team, we're actually working on trying to explain these reasoning models, try to understand where reasoning starts and stops. Like what is a reasoning step even? Because they blabber stuff along and you don't even know what a step is. So this is all ongoing research. The funny thing is they have just learned this from this MCTS data-driven approach. Right? So it's a very complex answer, unfortunately.
Okay, thank you.
We can take it offline.
Yes, okay, thank you.
So, hello. Actually, I wanted to ask about neurosymbolic models as well. Do you see a successor architecture to transformers? Like, not necessarily in the neurosymbolic, but because the little I know is that this architecture has not changed much since 2017.
Right.
So this is my question. Thank you.
I mean, the question is really interesting. And I've been working on this actually a long time, trying to replace transformers. It's very, very hard because first of all, transformers are kind of the ideal computational device for GPUs. You get a very high performance out of these GPUs. This is why they work. Like our brain is not densely connected, as I mentioned, right? Our brain is a more complicated structure than what we have there, right? So it's not an emulation of the brain. It's another thing that has, but I mean, planes are not flapping with their wings. So it's also clear that we don't necessarily always want to imitate biology. So it may be a more efficient structure. So I believe that these transformers, since they match our computational structures so well, and I'm deeply convinced that all of this is about computational performance, right? You will have an extremely hard time making any other structure performant enough to compete with transformers. Many people have tried, and I call this a gravity well. Some people call this the hardware lottery. If you Google for hardware lottery, it's the same thing, but it's not a lottery because they have been designed. They have been designed. Once transformers came out, every AI company now tunes their product to transformers because that's the market. The moment you are cementing this structure, right? Because you will not be able to, as a programmer, to do anything else performantly on your AI chip because that thing is optimized for transformers. Right? So forget it. I mean, it's going to be extremely hard. I'm not saying impossible, but very, very hard.
Thank you, Professor. Two quick questions. One, the period of time you've described in your slide from the transformer paper to 2024, we've seen this dramatic increase in performance of the traditional LLM models through the dynamics you've mentioned. Yeah. Do you expect a similar velocity of progress for these reasoning models? Is that something we can expect? What are the mechanisms that might drive that? And second question, again, very quickly, the transformer model, the traditional LLMs leverage the GPU architecture, the H100, Blackwell now. Are the reasoning models equally, are those chips equally appropriate for the reasoning models, or is there a chance for specialization in semiconductors?
Great question. So let me start with the first one, actually. The predicted rate of progress, it depends on your task. So for example, for the ARC challenge, these traditional models, they didn't do anything. They literally did not really improve because the ARC challenge just did not fit the kind of reasoning, or if you had a sorting task, right? Because it didn't fit the statistical distribution thing. Right? You couldn't just do next something prediction. However, these reasoning models, they increased it a lot within 1 year, basically. The ARC challenge is done at this point, right? So it's solved. So now it really depends on what you look at, because also if you now want to invent new things, I'm interacting with these models a lot. They blabber sometimes a lot of nonsense. And again, I would have shown it to you. You see there's a lot of nonsense coming. But at the end, they come to a solution. So they're extremely computationally wasteful. I believe that computational effort that they have to go through to solve a problem is a huge hindrance because that computation is expensive. Again, I would have shown you an example where I run Qwen 2.5b. Qwen 2.5b would have just said, oh, I would have used an example, square root of some large number. Qwen 2.5b would have just said, I use a calculator to do it. If you ask DeepSeek R1, it'll be like, oh, I run Newton-Raphson, and now Newton-Raphson is this and this and this. And then 5 minutes later, it has output 1,000 tokens, and it's still thinking. At the end, it'll get to the same result. Right? So that's a bit of a problem. Sometimes these models overthink. There are many papers about overthinking now because very simple things are now extremely complicated. So there are challenges. I would not want to speculate. Sorry, not a clear answer, but it's really more nuanced, multifaceted. Yeah. The semiconductor. Oh yeah, are these semiconductors well suited for these reasoning models? Yes and no. So we are actually in my group. We are working on optimizing the computational structure of these reasoning models to current semiconductors like GPUs. I think it's possible. It's not immediately there, but it's possible. I believe the DeepSeek team. I mean, they're absolute performance experts. They have probably done it. But it's not clear how far they will release that stuff. They release the weights, they release the model, but not necessarily the full training setup. So it's definitely a step.
Sorry, did I interrupt?
No, I guess.
Okay. Quick question. How do you define AGI? And of course, what's your forecast for this countdown?
Yeah, I need to remove AGI from this talk. So it was on the slide. I didn't actually say it, I think. So AGI is a discussion, whatever that means. So AGI stands for Artificial General Intelligence. I would like to rename it to AHI, Artificial Human-like Intelligence, because we humans are not generally intelligent. Because we humans are very good in simulating physics. We humans are extremely bad in performing large calculations. Like if you define intelligence as getting square roots of large numbers, square root of 758,992, my cell phone does this in less than a second. You guys will be busy for a couple of minutes, right? So it really depends on what you mean by intelligence. This is why general intelligence does not exist. In problem solving, depends on your problem. But human-like intelligence, I think these models can achieve. Does that kind of make sense to answer that question? I should really replace the AGI with an H, AHI.
Yeah. Yeah, I mean, we have seen larger AI-centered companies, including OpenAI, of course, pivoting away from this term as well.
Yeah,
so
absolutely.
I was a little bit thrown off and intrigued by mentioning of AGI in your deck.
Yeah, yeah.
So, in your opinion, what is the countdown? When will we see artificial human-like intelligence?
I would call what we have is already kind of artificial human-like intelligence, but it really depends. I mean, the problem is, does it pass a Turing test? The answer is yes. Like these models pass the Turing test. You can't differentiate them as a human from another human. Now, is that sufficient? No. So now I don't know. It's hard to define. I don't. Yeah, it's really hard to define.
So in this case, my last attempt to get an answer is. What is the next evolutionary step for AI? So if we remove this concept of AGI, which I agree, I'm on the same side as you, what will be the name if we have already achieved this intelligence surpassing human in some ways?
I have no idea. I really don't know. I believe that these reasoning models will get us to something that we would call real creativity and something that can amend scientists and make them much more successful. But I don't know what the next step is. I mean, this is now an engineering problem at this point. Like we know that we can combine these two things. We know this is kind of working. We just need to engineer it now to work well. Yeah, sorry, I won't give a.
Thank you.
You won't get an answer.
Thank you, Professor.
Yeah, sure.
I have a question about small models, because you have presented many and super large models, general artificial intelligence, and but there are a number of very small models that can actually run on your laptop, maybe even on your phone. So yes. What do you think about them?
The cool thing is that together with this reasoning chain, small models become more capable than larger models. So actually, you can now use smaller, slightly dumber models and amp their intelligence through these reasoning loops. So there is a huge unexplored or partially explored research area, how to now combine the two into the most efficient models.
Because they are task specific at that point.
Yeah,
and you mentioned there are mathematical problems that are super difficult, and so we specialize there. Then there are language problems, but then again, we are chasing specific tasks in some sense. And there is always something that cannot be just handled by just single models.
Yeah. And so there's no answer more than what I said from me. I mean,
okay, thank you.
Basically, I believe these small models play an extremely important role. I mean, at the end, what we are seeing as ChatGPT is not the full model. because it would be too expensive to serve. It's like a shrunk down version of the full model, an optimized version. And this is what's going on. Yeah, but it's very hard to exactly assess what's going on. Yeah, I think we need to move on now.
Here, I was wondering if we could go back to the beginning where you said that in the Industrial Revolution, human power became less important. And ever since, we've put a lot of less effort into becoming stronger, and we try to put a lot more effort into becoming smarter, into reasoning. So now that computers are going to take over the reasoning, maybe we should start to put less effort into becoming smarter and better at reasoning. But then the question is, what is your opinion of what we need to focus on next? What should we do after this once computers have taken over the reasoning?
I have just, that's a wonderful, I've just seen a tweet yesterday, is that we should go back to the bench. We should train muscles again. And the reason for this is not dominance, because in the past, I mean, it was dominance. Now it's health. You want to live a healthy life. And it's scientifically proven with a lot of evidence that you live a healthier life if you're physically strong. So that would be what I would recommend, you know, and that's optimized for health before the machines take over. No, I'm just kidding. So that would be my answer. Yeah. Oh my God. Yeah.
Hi, thank you so much for your talk. My name is Fer. So I have
Of course. So that is a huge open research question, and again, my group is working on it. The nice thing is now, if you use a process, it's called a process reward model essentially, right? So you now judge every step, and the nice thing is that these models, they may not be able to judge the output, but they can judge a step. Because how do we humans work? When I tell you I hypothesize something, I hypothesize that cancer can be healed, you naturally will be skeptical, right? But then I explain you how in small digestible steps. Like that's called a proof, like in mathematics, right? I give you a series of inference steps that you can digest, and at the end, I'm at my goal. This chain of thought and reasoning, MCTS stuff is exactly enabling that. These models don't do this today, right? They do not deliver proofs. What they do is they kind of give you small digestible steps that you as a human could follow. And then if you actually follow them half of the time, you're like, well, that's kind of silly. But now we have a way to kind of nudge these models. And this is exactly the research we're doing. I have no good idea how to do it, but we have a way to nudge them to prove these steps. For example, sorry, I'll take 30 more seconds because that's super interesting. For example, if you wanted to enable medical treatment. So I'm working with hospitals. And the idea here is that they have a language model that gives you a treatment plan. The nice thing in hospitals is that there are rules in countries that tell you what you should do, how you should behave as a doctor. Like if you see high fever, over 40, and the patient is vomiting, there is actually a rule book, which is more than 1,000 pages in the United States, that tells you. This rule book is often used to mitigate legal claims. So if you as a patient say, my doctor mistreated me, if the doctor can refer to the rule book, he's safe or she's safe, right? And now you can take this rule book and have the model give you the sequence of rules that it applied to come to the treatment. So that's kind of nice, right? So if you have kind of a rule book, an inventory of small steps that you believe are correct, then the model can reference these steps for every single step it takes, for every thought it generates, right? And this is what we do in the medical domain. Works really well. Funny thing is, every country has their own rule book. They're totally inconsistent. Like you would be declared dead in one country and alive in another country. So that, I mean, human rules are always inconsistent if it gets complex, but something like this.
basically something like RLHF.
Yeah.
Like, okay.
I mean, we do DPO most of them,
Yeah.
but it's like an RLHF variant, yes.
Okay, thank you.
Hello, everyone. Thanks for staying. We will start the second one. I will give a very short talk about my recent research. It's about causality. So just now, Professor talked about large language model, and everyone is surprised by how DeepSeek models, the impressive performance by those Chinese company. And for my part, let's change a little bit. If you care about real world, let's say in economy, you may care about how to improve the economic growth, how to grow the economy, and in healthcare, which factors really influence a certain disease. Then in those questions, I think causality may help you a little bit. So let's take a look at causal learning. Before I started, I may give a brief introduction about myself. I'm currently a PhD candidate at MBZ UAI, which is a new university in Masdar City, Abu Dhabi. And before that, I was a master student at Hong Kong, in Hong Kong University. And back then, I studied software engineering in China. So during my PhD study for the past 2.5 years, I'm fortunate to work with those AI leaders and causality leaders. So my advisor is Professor Kun Zhang, a professor from MBZ UAI and also Carnegie Mellon University. And I'm also a member of CIAR Lab, co-led by Professor Kun Zhang and our university president, Professor Eric Xin. And also, I work closely with Professor Peter Spurdis, who is a professor at CMU. And if you know causal discovery, and one of the most fundamental methods called PC is invented by him. So today, I will very quickly go through some exciting research topics that I did for my past PhD study. And I will mainly talk about some challenges in causal discovery or causal learning. And here's a few work that I've been doing and also collaborating with our other group members. And in the end, I also put other 2 works, not done by me, but by other group members. It's about finance and some challenging issues and methods, how to deal with in finance. And some another one is 3 demons in finance. Hopefully here they provide a systematic view of the issues and solutions in finance. Hopefully it can be of interest to some of the audience. Yes, maybe we can start with a very simple example. In Business Insider, they plot like this graph showing the correlation of chocolate consumption versus the number of Nobel Prize. So in this graph, you will see, probably the more chocolate that you eat in your country, the high probability that the country will get more Nobel Prize. So this figure might lead you to think that if in my country, I'm a decision maker, policy maker, I want to make more Nobel Prize. Should I increase the chocolate consumption in my country? Should I distribute more chocolate to our citizens every day? Yeah, it's kind of funny. Definitely no. So how could we explain this phenomenon? Is the chocolate consumption really leads to the number of Nobel Prize winner? Definitely no. Then how could we explain it? So here we use a causal model to explain the phenomenon. Here we call maybe a latent confounder influence the 2 things. Here it could be some economic power that can influence both of the variables. Let's say if you're stronger in economy, then probably, yeah, you are more likely to get more Nobel Prize. At the same time, yeah, since the country is rich, the citizen can afford to eat more chocolates. So here give us a kind of causal thinking of the real world observational data that we see. And how could we infer the underlying structure of the true pattern in the real world? So this graph really tells us that correlation is not causation. We really need to go into the causal level to infer the true structure and to tell us the true reason there so that you can better make decisions. So let's very quickly go through what is causal discovery. I think some members interested, we heard a lot causal discovery, causal inference. Then causal discovery is the most fundamental task in causality. So basically, it just input a tablet data. It's what we see in real world. We have some variables, we have some observations. So in the end, we want to get a causal graph to let you know how those variables influence each other. So in the middle is the causal discovery methods that play in the role. So in general, there are three major categories in causal discovery. First of all, is constraint-based, just using some conditional independence to finally get the causal graph, and some other score-based method, and also functional causal model-based. They just assume a very strong distribution or function in the data so that you can finally get a causal graph. So here's the key insights here. So if you go to the machine learning community, you may heard a new term called causal representation learning. So what is the difference between causal representation learning and causal discovery? So here in real world, we will see many high-dimensional data sets like image, text, and time series data, audio. All those things are high-dimensional. But in previous causal discovery, just give you a table. It's single variables. However, here is high-dimensional. So in causal representation learning, we care about how those high-dimensional data causally connected to each other. So in this task, we mainly will do a representation learning. We will learn a hidden variables behind all those high-dimensional data, and later on, we will see how those latent variables connecting to each other. So here is the one graph we plot in our paper. We have a huge data set collaborating with another institute. There are a bunch of human information like founders, all those are images and tabular data, and also the time series like sleep and heart continuous data sets. Yes, so just now I just give a quick view about what is going on in causality and in machine learning. Those tasks are what we really care about. Then, yeah, let's take a look at what I've been doing to solve those major issues and what major issues are there. So one, our recent work is about deterministic relation. Actually, this relation is everywhere in real world, and it's really annoying because once you have those relations, a lot of methods will fail. Why? Let's take a look at this example. Let's say if you're doing causal discovery of those variables, there are 5 variables, and there's X, and you have an identity copy, which is deterministic, right? Because X prime just equals X. Once you have this in your data set, you will find that no matter what is here, here triangle is any variable that you have. So given those identity copy, this previous X variable will always be conditionally independent from anything else. So with this property, it will cause a lot of issues because in previous causal discovery method, they heavily rely on this property. They will use this property to remove edges in their methods. So in the end, with this property, you will find that all those deterministic relations have nothing to do with all the rest variables. They are isolated, which is definitely wrong. Then here's another example. Actually, this example is inspired us to develop new methods. We got some demographic features from human, and we want to analyze how those features related to certain disease. So we find that, yeah, we have height and weight and BMI. Clearly, you will see a deterministic relation here. And Using previous causal discovery method, we find that those variables are isolated from all else. So you can see, yeah, it shares similar insights here. Once you have deterministic relation, it will get ruined. You will not get informative edges later on. So how could we deal with it? Certainly, a very naive way is I just simply remove them. I break the deterministic relation. I just remove them so that everything else would be fine. And you could go with a normal discovery method. But let's get back to our machine learning principle. As a machine learning researcher, we care about data. Data is the treasure and we just want to make as much as possible to infer the knowledge that we want to get. So for sure, we don't want to throw out anything. We want to keep everything. So the problem comes, if we keep everything, how could we make use of such information to go further and get a reliable result? So this motivates us to develop a new method. Here we are called a deterministic GS. Here, GS is another typical method in score-based causal discovery. So here, there are two graphs. One is the ground truth causal graph. So you will see it's here, the three parts, DC is a deterministic cluster. So those variables are deterministically related to each other. And those are just normal variables. They have extra noise. And those bridge set is those edges connecting the two parts. So we find that, yes, score-based method actually have some potential ability to get a not too bad result. So you will see this is the result get by score-based causal discovery method. So you will see, yeah, all those bridge set will still maintain here. They will not disappear like previous PC methods, but you will see some redundancy here. For instance, V1 points to V6. So this is due to some properties of score-based method because they try to explain the dependency in data. Then when you're doing the method in the very early stage, this edge will be added. So then it's hard for you to remove them. So we found this interesting phenomenon, and we made a further modification is that we still detect the clusters in the first, and then we made a tiny little bit modifications. And those modifications were revealed in the 2-stage of GES, just very tiny little bit modification. And then we will do some post-processing. So the post-processing is just to remove the redundant edges. I'm not going into the details, but the general idea is that we, based on existing method, did some modifications and have post-processing so that we can get a general framework of a causal discovery method to handle real-world case. And later on, we proposed some identifiability conditions. If you go to causality community, you will hear a lot identifiability. So I will briefly introduce this. What is identifiability? Once you have a data, you always have a true underlying unique structure. For instance, either one. Then in some cases, you will recover multiple possibilities. For instance, here, 1, 2, 3, they are deterministically related to each other. And one possible outcome would be 4 connected to 2 and 3. And since they are deterministic relation, they can be equivalently replaced by the other 2, like 1 and 3 pointing to V4. So in this case, it's not, we call it's not identifiable because there are multiple possibilities. However, in this case, it's identifiable because this is the only case that explains your data. So this is what we call identifiability. So we list those conditions to ensure our identifiability. So this is a theory part. So I will skip. This is some real-world cases. We always focus on real-world and inspired by real-world. And actually, this application is we want to identify how rheumatic disease related to demographic features. And so we apply our method, you will see there are certainly deterministic relation like BMI, height and weight. However, using our method, you can still recover some clear dependency between them. Yes, that's one challenge, which is deterministic relation. Let's take a look at another challenge, which is heterogeneous data. I think in finance, there are a lot of heterogeneity in the data. And at the same time, in real world, there are decentralization issues. Let's imagine in different cases, like biological company, one company that we collaborate with, there are multiple offices, like in Israel, in Abu Dhabi, in Boston. And for each office, they conduct their research independently. So once they collect so many data sets, how could we make joint force of all those data sets and get more reliable, insightful results? So there are actually two challenges here. One is data privacy. For instance, some e-commerce platform, all those information about users is quite sensitive. You cannot directly distribute all those user information. At the same time, the data can be large amount. If you just simply distribute the raw data, that was so costly. For sure, you don't want to do that. So what could we do? In this case, we propose some summary statistics. The key idea is that you have a bunch of volume data. So can you summarize those data and extract some key features in those data so that just rely on those summary, we can do something. And rely on those summary, that's all we want to conduct our discovery or machine learning tasks. Yeah, so that's how we propose a covariance matrix. Actually, it's 4-dimensional covariance tensor. We call it tensor. So with this, we can conduct previous or just original causal discovery method. They will start with skeleton discovery, and then finally, we will find the directions here. So here, we mainly want to tackle with the real world issues that data sets are distributed at different locations. At the same time, they have heterogeneity, or we call distribution shifts. Yes, so this is another challenge. Recently, we also look into some gene data sets. Gene data sets is also annoying because there are so many dropout issues. And it's first of all, it's hard for you to measure. Second of all, even though you measure it, there are a lot of measurement error. And another issue we find that most people overlook is a selection bias issue. Because in living cells, possibly there are 2 genes. They might be functioning guided by some other underlying factors. So here we call it's selected by other something. So here it shows that if we intervene on something, the distribution will change. So here we want to do causal discovery. There are 3 major cases that we want to handle here. If there are direct cause, if we intervene X, then you will see there is some distribution change in Y. However, if you intervene on Y, you will not see change in X because here is a direct change here. However, in selection cases, if you intervene either X or Y, you will see the change on the other side. This is the property of selection. And we also covers the latent confounder case. Since it's latent confounders, even though you intervene on X, you will not see the change on Y. So clearly you see the difference between the 3 patterns. And we just make use of these tiny differences to infer the accurate structure that we want to see. So selection bias is the key issues that we want to handle here. Yes, the previous work, we all focus on single variables, just single dimension. However, in real world, just as I showed in the beginning, the data can be text, image, or time series, or audio. So in this case, how could we infer the causal relations from those high-dimensional data? Here is an example. We also worked on real data sets. We collect some eye fundus image. So it's the right eyes. And here is 3 latent variable of left eyes. And here is some latent variable of sleeping. And you see some interesting pattern. Age is in effect the eyes. Age clearly affect how your eyes look like. As you're getting older, definitely there's subtle changes. And one more interesting thing is that you will see the hand grip strength actually have some correlation to your right eyes. This finding is quite interesting, and it's verified in previous research. I think it's also feasible because if you look into someone, if his eyes so determined or really powerful to look at you, probably is stronger in strength, probably. So that's how the hand grip might be correlated to the eyes. Yes. So in this work, the key issue is that all those latent variables, they are connecting to each other in a nonlinear manner. In previous method, for simplicity, they just assume it's linearly correlated to each other, but that's definitely not the case. So in this case, we extend, in theory, to a more general setting, which is non-parametric setting. We allow the latent variables to be non-linearly or non-parametrically correlated to each other. So yes. Here is the another one is how we deal with latent variables in either economy or finance. In biology, there are a lot of latent variables, and in this setting, we just extend it a little bit, because in previous latent variable, we just assume it's hidden behind the observed variables. However, the setting can be general, because observed variable can also influence the latent variable, and then latent variable influence the observed, vice versa. So we extend the setting to make it more general, more closer to the real world. So we develop those method, general method, to Big Five personality analysis. This is quite interesting. Big Five personality traits is developed by a statistician some time ago, and it mainly explains 5 dimensions of one's personality. So in this data set, they collect several questions using questionnaire. For each dimension, they use some questions to see how strong or how weak your personality is. So here, using our method, you will see that, yeah, for each question, they are strongly clustered to each other. At the same time, they find some interesting pattern behind those underlying clusters for each dimension. Yes, I'm not going into too much details here. If you're interested, I will put all the reference here. So this is the last one. I think it might be interesting for some audience. It's about, we discuss some challenging the demons in finance. Actually, there are 3 major issues that we see. One is mismatch in time resolution. Another one is the data set non-stationality. And also there's some latent factors. All those 3 are major issues in finance. So we kind of propose a systematic view to understand those issues, at the same time propose a reliable solution to handle all those issues at the same time. Yes, so this is a graph of the stock price of Pfizer and Boeing, and clearly you will see the heterogeneity or non-stationality in the stock price. Yes, that's all for now. That's all for my part, and here's the reference. If you are interested, feel free to take a look, and I'm happy to take questions. Thank you.
Any questions?
Yeah, I have a
Thank you.
question. I'm remote, sorry, but I'm working at ADIA QRD with Q. Because you raised a big challenge at the end of your presentation. First, congrats for your presentation. It was super good, very interesting. Do you think that it will be one day possible to capture time varying causality in the sense that, as you say in finance, there may be some causality that can be elusive, that can appear and disappear. And if that's something that can be realistic or it will never be solved, that means that the only way that we can capture causality is super solid deterministic relationship in a sense of the law of thermodynamics, for instance. And that's the only way we can capture causality.
Yeah, thanks for the question. Yes, great question. I think to make it short, I would say yes, there is always a way to keep track of the data. And you see, let's put the question in another perspective. You say whether we can or we cannot. But if you do to see from statistical view, we always use like p-value or like statistic to see how strong the dependency is. It can be a value from 0 to 1. So rather than say it's yes or no, we would say how likely we can detect the dependency. So we can always get a value. It's between 0 to 1. So it can be very tiny, very weak. But if you see those weak signal as a dependency, yes, you're right, they are dependents. But if you put your threshold very high, then you will see no, they are not. So yeah, my intuition is that we can always have a value to see how strong the dependency is. Then it's you decide whether they are dependent or independent.
Yeah, I agree. Okay, thank you.
Yeah.
Thank you, Luca. How about we move to our next speaker? And we can take questions after this. I'd like to welcome Khalid Al-Naimi, PhD student at Khalifa University on stage. Thank you.
Assalamu alaikum, everyone. Thank you, ADIA Labs. Thank you, ADML. Thank you, Fatma. Today I am here with my team, Gote Marti, Matthew, Abdullah Al-Kitbi, and myself, Khalid Al-Naimi. We're here to present for you the second study of a trilogy study, if you will. And we'll go through the background in the next couple of slides on where is this coming, what are we trying to do, and all of that. A quick overview on what we will cover, the background, then we'll jump right into the study to talk about the task definition, experimental setup. We'll look at the results, we'll do some result analysis, and eventually we'll conclude. A quick background about myself. I have a background in data science and computer programming. I work in ADIA. I've been there for more than a decade, and most of the publication or the work or the studies I've done is in the computer vision and lately in the NLP field. My PhD research is focused mainly on using natural language processing tools on financial documents, whether to extract meaningful features to do investments or try to create AI agents and whatnot. This part is really important, and this is how we got to this paper that I'm presenting. Last year, my colleague Abdullah led the team to mapping Hong Kong financial ecosystem. So we're looking at Hong Kong, and the plan is to map it. So we're looking at entities, financial entities in Hong Kong. We're looking at the people who work, who have license, what type of activities they can do and what they cannot. But we also wanted to expand that data set. The data set initially was not available, so the team had to scrape it off the SFC website. We created the data set. A couple of slides later, we'll look at what is in the data set, but we wanted to expand that to understand more about the ecosystem. Who is there? What are these people, the professionals? What's their nationality? What's their country of origin? What's their age? What's their gender? And all of these type of, call it features or attributes, is not something we have. So we used LLMs, but we did not test how good are LLMs to create these features. In this study, we look at data sets that are annotated, and we test multiple LLMs, as you will see soon, to know how good LLMs are in doing this. This is important for social science, public health, and public policy, but the idea could be taken to any other field if you have the time and effort to put and test all of these LLMs. So jumping right into the task description, what is the goal? Predict demographic attributes using only the name as an input. So we pass the name to an LLM. We tell it, okay, can you give us the country of origin, nationality, gender, race, birthday? How do we do this? We use frozen LLMs for zero-shot predictions, and we have a very specific prompt structure that you can see on the right side. So this is literally the prompt structure. We thought about it. We made sure that the answer we get are in certain types. So the race category, male, female, we standardize the outputs, nationality, country of origin, and you can see even the birthday kind of format. The expectation we get all of this back. So what did we scrape from the SFC Hong Kong dataset? This is exactly what we had before. We take the full name, we pass them to LLM, we get back the predicted nationality, gender, ethnicity, age, and country of origin. We always keep the full response just to test how much we need to parse to get the correct numbers back from the LLM. I'm sure all of you work on machine learning and work on many different data sets. As you can easily see, the idea could be replicated in any field. What's the most important is to actually test and see how good are LLMs in doing it. So what we did in this paper, just to test the LLMs, we found two data sets, the Florida voters registration 2022. The lighting is good, huh? No, make it dark. Maybe it look like a movie. People get popcorn. It's fine. And as you can see, if you have the data set, the most important thing is the annotation. So we have the gender, birth date, and race, which is something we can test the LLM because we have the annotations. And we have the Wikipedia person's data set. And what we have there is the nationality. So when we ask the LLM to predict nationality, we can easily check whether they're predicting the correct nationality or not. And obviously, the Hong Kong, as it was scraped, we have nothing here. And we'll see how did we think about it, how did we try to solve this problem. We did very minimal cleaning on all of these, Florida data set. We followed the previous study. We reduced categories to 5, and we did a small number of cleaning on Wikipedia. We did voting mechanism using LLMs to test whether this is something that is not true. So you'll see a horse with a name. It's a horse, it's not a human. So we removed that. This is the data set of the Wikipedia. As you can see, it's not really that balanced, mostly American. And then if you see the gender on the Florida voters data set, you can also see. And this is one of the reasons why we use the F1 macro for accuracy, which is the harmonic mean, which deals with the imbalanced data sets. We try to be creative in the LLMs we try to test. We test a total of 12 LLMs across different companies, Mistral, Meta, Google, Cohere, Anthropy, and OpenAI. We also, in each company, we try to have a big model, smaller model, open source, closed source. So our testing the result of our testing can be meaningful. As we said, the prompt was used across all the data set. And as we mentioned, these are the predictions because of the annotations and how we will test them. We did minimal parsing. I think 3 models, which are heavily instructable. They didn't really respond much to certain type of prediction attribute, mostly age. And then for evaluation, we used the accuracy of 1, as we said, and the mean absolute error when we used numericals, which is age and date of birth. So when we look at the gender predictions, these are all the results that you can see. Obviously, there is high accuracy in predicting whether a gender from only the name, again, just to make sure, only from the name, the accuracy was really high. We also had the ensemble 12 LLMs. So this is a complete accuracy of all the LLMs. And we did also 3-shot learning. We did 1-shot, 2-shot, 3-shot, 4-shot, and 5-shot, but we are reporting 3-shot here only. and the performance was really strong. When we look at the performance of the predicting birth of date birth or the age, overall all LLMs really didn't do well. They are not reliable. What's interesting is a lot of LLMs, they gave a much historic age. If you see these between the parentheses, this is how much further they are in predicting age. What's interesting is Gemma, completely the opposite. It predicted much younger people. But in general, overall, LLMs are not really that good in predicting age or date of birth. When we look at the race predictions, it was good accuracy overall, still beating very traditional models, but on par with machine learning models such as LSTM or ResBERT. I won't go in much more detail here, but overall, good performance. And when we look at the nationality, would say also the same thing. Not really great performance, but not bad. Still a good performance overall. And now, how did we test the Hong Kong? We don't have the annotation. So what we thought is, can we do an LLM agreement? All of these LLMs, we tried to see how much they agree with the output. And as you can see, there is a huge LLM agreement on the ethnicity. And as you know, ethnicity is non-orthogonal. So we try to use another measure, which is cosine similarity. We got the vectors of the ethnicities, and this is how we compare these numbers. We did the same with age, and there's so much non-correlation between all the models and very low agreement overall. So this kind of gave us an idea of how good LLMs are at trying to predict these type of attributes. So what is really the key findings? LLM have good accuracy in predicting certain demographic, really good at predicting gender, good at race, struggling so much with the birth years and age. Maybe one thing I didn't mention, they always gave back rounded age. So 90, 95, 100, they never gave like in between or almost never, which is interesting to do further analysis on the biases of LLM. Overall on par, if not better than previous ML models. In samples, when we ensembled the top three, mostly didn't really give better, helps a little bit, especially on the birth dates, and few shot learning helps a bit, but not really that consistent. Maybe 10 shot would have made a difference. Overall, closed source model performed better than the open source model. What's the key contribution of this study? Outperformance of early studies using the same data set. We uncovered biases. There's much more detail in the paper. We'll send the link to it. And we published all of this data set on Kaggle for further work for all the people who are interested in this field. So what is the future work? We want to expand this idea where we do LLM data enrichment applications, specifically on the financial domain data sets. This is where I work, and this is mostly where I do research. And so we need to keep or want to keep monitoring the strength and biases of LLMs. There are new LLMs, a new version of LLMs. DeepSeek is coming out, so maybe we'll add it to the list and we see. This is the most slide I like. No need to, when we think about data LLM enrichment, I don't want anyone or myself even to limit myself to text. It could be audio that is cut between a conversation that LLM could generate, or even a video or an image, an old image that you lost some. Maybe LLMs are good at recreating this. So audio and visuals should be something in mind when we think about these things. And don't be scared to share your name. People might know more than you think. Thank you very much, and I'll open it for questions. Yes.
Thank you for your talk. Why did you think that the name would be correlated with age?
Well, we didn't think that's why we tested. I can elaborate more of.
No, because
These are,
I thought that you had an assumption, and you wanted to check, like because I thought maybe you thought that someone has, for example, in Italy there are some names that are out of use. Okay,
True.
so the fact that someone has that name is pretty. It's a very good indicator that it is someone who is very old.
Yes, yes.
But the problem is that you have a lot of names that are used by people that are old and people that are not old. So that's why I was a bit.
No, thank you. You're very right. I think also I just want to mention we shouldn't forget the main idea motivation. We're trying to map out the ecosystem of Hong Kong, and if we have age, it will give us more idea and information about people moving from one company to another company, or leaving certain sector to another, or even the country. But it's one of the attributes we wanted to check whether LLMs can do it. But totally agree, certain names have been used a lot at certain period of time in history, but then they pop out from time to time, and I think that's why LLMs didn't really do well on that. Thank you.
Can I? It's related to that question, but expands a bit more. So a name is just a label that we put on a distribution of people or a set of people. And of course, LLMs see this information through text that has been used to represent them, to address them. And so in some sense, the age is a sort of average of that distribution, because if you will ask the same question, you will get most probably, we know they are stochastic LLMs, the same answer in terms of age. But then besides this observation, it was the difference between the different LLMs that you tried. And I'm a little bit surprised that basically there is not much variability, or at least in some question, and you can expand, maybe you comment a bit on that. So I expected biases if you have an LLM that is either they are all trained on the same material, or maybe they should show differences, especially related to names, which is something very geographical.
Very true. We suspect early on that LLMs might have actually learned all of this from the data that was given to it while learning. And you're right, we didn't see any big difference when it comes to gender, but the birth dates are really very interesting. Not only, we thought that large language model were trained more on historical data. That's why most of the predictions were historical, but then we were kind of surprised when we look at Gemma. Maybe one of the things I didn't mention when we chose this large language model, we also chose Asian-based large language model because we're looking at Hong Kong data. We thought there might be something there that these LLM, how they are trained on different language and different data sets. I hope that kind of answered what you're looking for.
Did you check if the test data?
No, we haven't tested that, but it was on our list of things that we could look at in the future. Yes.
So how far into prompt engineering or in context learning or fine tuning did you go, and are you going to go? I mean, if you want to make this a product, right, there are 1,000 options you could take.
Yeah, I mean, there are many ways well, first of all, I think you mentioned the prompt. We didn't work much or focused on the prompt engineering itself as much as you would want when you really are looking to answer a question to a certain level. But I think what we made sure is, okay, we're using 12 LLMs. We want to make sure what we can compare all of them correctly and properly. So the engineering part was more of how can we do a prompt that all of these LLMs, when they come back to us, we can compare the result. More of that part of
I see.
look.
I see. Okay.
But if you're to answer the second part, maybe if not the third, how can we expand that? One of the things is, can we connect the names to pictures, which will make it a million times easier to at least do gender. I'm sure pretty much also age because of facial expressions. I think this is maybe is motivating you to think more about certain things. Where could this be if we want to take it to a product level in social science or public health or policy or all of that?
Yeah. Yeah. Cool. Yeah.
Thank you. Yep. Here and there. Yes, Professor. He's my professor. For sure, he have. Give him 2 mics, please.
No. He's joking. He's joking all the time. A name is very little to grind on for an LLM. Did you think of, or what's your thought for the future for giving more text-intensive data sets to this task?
I think for here only, we only pass the first and last name. I'm sure if we pass more information and probably put it in a context, because part of the prompt itself is also knowing that these are working in Hong Kong.
Yeah, but what about the classics like housing price prediction, where you have maybe now also lots of textual description about the neighborhood, about the city, all this data that is available in form of text.
Yes.
That's something. There's a lot more to grind on for LLM, right?
Yep.
So names are very, very small things to do all these predictions from. You have so much more. The world is open now.
No, true. There are many applications of the idea itself, like how can we extract
electronic health records.
Yeah.
Okay. Right.
Okay. No, it's okay.
So I have a quick question. So you're trying to predict the age using LLMs, but wouldn't it be better if you predict a birth year? Because some LLMs are trained on like 2020, for example, and others are trained in 2023. So models that were trained on 2020 will give you the age of the person at that time. So do you see what I'm trying to say?
I see.
So did you account for that, or like what was your way of getting around it?
We thought about predicting age. We initially, when we did age, we did birth of date. We didn't see a difference. So we went with birth of date because that's like how it is presented in different papers in the same field. Yep.
Yeah. Okay. Thanks.
Thank you. Yeah. Thank you very much.
Thank you everyone for joining us today. I would like to take this opportunity to thank ADGM Academy and Abu Dhabi Machine Learning and ADIA Lab team for organizing such an inspirational seminar. Thank you also for being here today. Great discussion and great questions. Please stay tuned for upcoming seminars. We have also next week another seminar, and we will be updating our social media pages, inshallah, regularly. Thank you.